Hello everyone, I'm very glad to present SiWa, which is a novel device for seeing into walls using ultra-wideband radar. My name is Zheng Tianyue, and I'm from Nanyang Technological University in Singapore. The basic idea of SiWa is simple. We let a user to swipe the probe of SiWa on the wall, and by analyzing the reflected signals, SiWa can perform imaging and material identification. Traditionally, if we suspect something is going wrong in the wall, we either drill the wall open for sensor embedding or use ground-penetrating radar to perform imaging. But the drawbacks of these methods are obvious. For drilling, we actually crack open the wall and we damage it. For ground-penetrating radar, we can see the device is very bulky and not convenient to use. Therefore, we resort to wireless sensing and especially RF radio frequency sensing for seeing into walls. We tested different devices. For example, first we test Wi-Fi. We find that although Wi-Fi can penetrate the wall, excessive diffraction makes it unable to locate the in-wall structures. For AR UWB radar, we can see the signal on one hand can penetrate in the wall. On the other hand, it can accurately reveal some image information of the in-wall structures. For the FMCW radars on the sub-millimeter and millimeter wave bands, although the resolution is great, but they are reflected on the wall surface and cannot penetrate the wall. Therefore, we choose to use IR-UWB radar in SiWa. The workflow of SiWa is as follows. First, the hardware collects the two-dimensional signal matrix for further processing, and we want them to perform in-wall imaging, which provides a map for locate in-wall structures. After that, we can identify the materials of those in-wall structures. Before telling you any theory, let me model the signal. So the transceiver sends out a modulated Gaussian pulse into the wall. As the user swipes his hand on the wall, first, the distance between the probe and the target is large, so we have a large time of flight. As the user moves his hand toward the target, the time of flight decreases, and as he moves his hand away from the target, the time of flight increases again. If the user moves his hand at a uniform speed, we can find a hyperbola in the two-dimensional signal matrix. Traditional imaging algorithms actually collects the energy on the hyperbola and focus it back to the target point. As we can see in figure A, so the bright spot is the focused energy from the hyperbola, and we can observe two targets in the wall. But the drawbacks of this algorithm is that it requires calibration. Some parameters has to be estimated beforehand. If they are not estimated correctly, we can see that the imaging results are blurred, as shown in figure B, or show some strange patterns, as shown in figure D. Let me take a look at the conventional design for material identification. We leverage the idea called polarimetry or ellipsometry to perform material identification. The basic idea is that if the electromagnetic wave is reflected back from the target surface between the target and the wall, the polarization direction will be changed. And by observing the copolarization and cross-polarization components, we can characterize different materials. For example, here we can see in Figure A and Figure B, the characteristics of rebar and PVC pipe can be differentiated. To summarize, the problems faced by model-based methods is that for imaging, the range migration algorithm needs calibration, and if given the wrong parameters, the imaging results can be really blurred or even deliver the wrong location information. And for material identification, the environment can have a really great influence on the result. For example, the wall materials, humidity, temperature, or even the depth of the involved structures. So to overcome this challenge, we propose a deep learning approach for SiWa. Basically, after getting the two-dimensional signal matrix from the hardware, we use a deep learning neural network called INET to perform imaging. And the imaging results are used as a map to pinpoint the exact location of involved structures. And we further use another deep learning neural network called MNet to analyze the signal of that spot and perform material identification. For the imaging network, also known as INET, we employ an encoder-decoder network. Firstly, a convolutional encoder encodes the two-dimensional matrix into the latent space, and later a decoder network, which is composed of ResNet blocks, interpret the features on the latent space to the imaging result in a nonlinear fashion. So the benefits of using deep learning to perform imaging is that it can be more robust to parameter changes because we don't have to estimate parameters such as hand motion speed and permittivity of the wall beforehand. We can just input the two-dimensional signal matrix and it can do imaging automatically. For material identification, the network is called MNet. So after extracting the one-dimensional signal from that spot of interest, we leverage a one-dimensional ResNet to classify the materials. And as we said earlier, because the environment has a great influence on the classification result, we use an environment discriminator to remove irrelevant features on the latent space, thus improving the identification accuracy. To implement SiWa, we have to pick the right antenna. We tested different antennas and find that the log periodic antenna is reflected least at the air wall boundary, while it delivers the most amount of energy into the wall and penetrating the best. So with the right antenna, we design a dual polarized probe with two orthogonally placed receive antennas to provide the hardware for ellipsometry, which will be used for material identification. We tell the SiWa in different environments. For example, in office environments and even in a precast concrete plant. We also test different materials. Next, we come to the evaluation part. To give you some intuition, on the left-hand side, we have this concrete block with several rebars embedded. The distance the spacings between the rebars are marked in the red lines. On the right-hand side, we have the imaging result. We can see that both depths and horizontal distances of the rebars are correctly recovered. To quantify the localization errors, we provide the cumulative distribution functions. We can see that for both depths and horizontal errors, the median is below 1 centimeters, which is quite good. As a comparison, the traditional range migration algorithm delivers nearly perfect result if the parameters are correctly estimated. But in practice, no parameters can be estimated perfectly. If any parameters are slightly deviated from the ground truth, we can see the results are pretty bad, as shown by the dashed lines here. We also study the relationship between localization errors and various environment and operating variables. We see that although different environment variables such as water content, depth, hand movement speed, and materials influence and degrade the imaging performance, but even in the extreme cases, the errors are still acceptable with a median error below 2 centimeters. Next, we evaluate the classification performance. We evaluate both material classification and diagnostics. So material identification means we identify the materials if it's a rebar or if it's a water pipe. And diagnostics means we evaluate, we want to tell its status. For example, if a rebar is corroded or not. We can see that the overall accuracy are mostly above 90%, which is pretty satisfying. We also study the environment influence on the identification and diagnosis accuracy. We find that even in the extreme cases, the accuracies are above 80%, which is good for everyday usage. At last, we compare MNet with other networks. The MNet with an asterisk is a similar network without the environment discriminator. So we can see if the discriminator is removed, the identification and diagnosis accuracies are dropped by 3 and 6% respectively. And MNet outperforms both two-dimensional ResNet and multi-layer perceptron by a large margin. We also evaluate the latency of MNet on different devices. We find that even on Raspberry Pi, the inference latency of SiWa is 0.69 seconds. So this demonstrates that SiWa has the full potential to be integrated in a handheld device and will be used in field tests in the future. Okay, thank you for watching my presentation.